Okay, so this is just an order of operations problem with fractions instead of whole numbers. So where do we have to start? Okay, well, we'll go through the steps. You see parentheses, you got more than one thing at the same level, so we go left to right. We find that one first. But in there, we still have to look for order of operations. So you're right, we do end up inside this other set of parentheses. What do we have to do in there? Subtract. 2 and 5/8 minus 2 and 1/8 is? Careful. Just 1/2, right?
Oh, yeah.
Yeah. So 1/2. And we've reduced what's inside the parentheses to a single number, so I can get rid of the parentheses. That's if I can write. Now what do we have to do? Multiply. 3/4 times 1/2, which is 3/8. What's that?
Now it's 1.5.
So now we add 1 and 1/8 plus the 3/8 is 1 and 1/2. We're going to take out the parentheses because we're down to a single number in there. And then, I heard someone start to say it. 2/3 times 1 and 1/2 is 1. Then 3/4 minus 1, or 3 and 1/4 minus 1 is 2 and 1/4. Anybody have 2 and 1/4? Cool. Okay, so questions out of the homework. You said unit 15. Little book. There are a couple of things in Unit 15 that they included that we really haven't talked about yet, and I'll point out what those are. That's one of the things I've been a little frustrated with these books. This little book is supposed to follow your big book kind of closely, and for the most part they do. For the other programs like carpentry and welding and stuff, they do. But this book, for some reason, throws little extra things in there every now and then. So the one little extra thing that this book threw in on this assignment, we had a few problems. They look like this. Well, technically we know how to do that, sort of. But this is notation. This is actually scientific notation, which is something we'll talk about here in a couple of weeks. So if you didn't get the problems that look like that, I'm not worried about it right now. In fact, today we're going to talk a little bit more about the powers and the roots and how those fit together. So are there any problems that didn't involve a power like that you had any problems on the homework that you want me to go over? Okay. On Friday, I gave you that quiz 3 with decimals. And I told you to keep it over the weekend and bring it back in today. If you guys need a couple minutes to finish that up, anybody have any questions on that they want me to answer? Then you also had the quiz 2. The quiz 4, sorry. That one ready to go? Give me just a second here, I'll pause. So our new topics for today. On the quiz 4, by the way, we'll have some homework, extra time at the end of the hour to work on that, and we'll get those handed in probably before you leave today. Our new topic for today, we want to talk about powers and roots. You know, we've seen things like this, 8 to the 3rd power. What does that mean? That means, yes, repeated multiplication. That means 3/8 multiplied together, or 512. Do all of you know the button on your calculator that does that? Depending on your calculator, many of your calculators have a caret key, looks like that. For the TI, that would be over on the left-hand side, about halfway down. Some of you might have a y to the x key, looks like that. Others might have just a key that looks something like that, or an x with a box next to it. So I want you to try to figure out 8 to the third power, get that entered. You would type in the 8, press whatever key you have, and then the 3. So let's get that figured out quick to make sure that works. So then I'll ratio 5 to the power of 6.
I got it first. That doesn't say it.
Okay. 15,625. How about this one?
Oh, of course.
2 to the power of 12, 4,096.
Do you even think about this, or you just?
You got it memorized.
Just.
Well, I've told you before, math is about patterns. And once you see the patterns, the calculations are very, very simple. I mean, there are certain basics I have memorized, and from there you can build patterns. Fives are very simple because any power of 5 is always going to end in 25. So you've got 25, you've got 125, 625. All the powers of 5 end in one of those. So the rest is just multiplying out the lead digits. For powers of 2, I used to do computer programming, so you know that 2 to the power of 10 is a kilobyte. It's 1,024 bytes. So from there you can build. It's real easy. 2 to the power of 12 is just 2 to the power of 10 times 2 twice, so times 4. And it's a simple multiplication to 1,024 times 4. So there's a lot of patterns in math that once you start to see them, the calculations are really simple. The problem is you can't teach the patterns because everybody sees a little bit different pattern than others. And your mind works a little bit different than, some people's minds add extra pieces on, work with it, then take those extra pieces off. Other people take off to get down to a set standard, work with it, then put the pieces back on. And so everybody's mind is a little different. So we can do those powers fairly easily, but let's take a look at something like this. Negative 3 to the power of 4. Did you get 81, or did your calculator try to tell you negative 81? Why would it try to tell you negative 81? Well, remember we talked about our order of operations. If you just put in negative 3 to the power of 4, your calculator is going to take 3 to the power of 4 and then put the negative in front of it. So you do have to have parentheses around that negative 3 when you enter it. And then it should come out to be positive 81. Because if you think about it, this is negative 3 times negative 3 times negative 3 times negative 3. Well, I'll multiply the first two. Negative 3 times negative 3 is a positive 9. Positive 9 times negative 3. Well, positive times the negative is a negative. 9 times 3 is 27. Then negative 27 times negative 3. Negative times negative is a positive. 27 times 3 is 81. In fact, after looking at this, what can we say about anything to the power of 4? So, well, anything to the power of 4 will be positive. Negative 7 to the power of 4, 2,401, will be positive.
Is there any even power?
Well, let's keep looking at it. Then we'll see in a minute here.
Now, 81 negative or
It's positive. So how about negative 5 squared? Well, if we think about it, that's just negative 5 times negative 5, right? So that has to be positive 25. Negative times negative is a positive. And 5 times 5 is 25. Negative 8 squared. Positive or negative? Positive 64, yes. Looking at this, we can see anything squared has to be positive because anything times itself, either it's a positive times a positive, which is positive, or it's a negative times a negative, which is also positive. So anything squared will be positive. Yes. Most of your calculators have an x squared key on it. If you use that, you don't have most of your calculators don't have to have parentheses around the negative for squaring it. But check it out and make sure you know how your calculator works, because each one does work slightly different. But anything squared better come out positive. So how about negative 5 to the third power? Yeah, as we look at this, negative 5 times negative 5, negative times negative is a positive. 5 times 5 is 25. But now we have the 25 times negative 5. Positive times a negative is a negative. 25 times 5 is 125. For the third power, it is possible to come out to a negative number. A couple of you have said it now, so I'll give in. If the power is even, the result must be positive, always. If the power is odd, then the result is the same sign as the beginning number. If we started with a negative, if it's an odd power, we're going to end up with a negative. Now, obviously, anything that's positive, it doesn't matter what power we take it to, it's going to be a positive result. So we're only talking about negatives when we deal with that. So negative 3 to the power of 5. First of all, positive or negative result? Negative. So then 3 to the power of 5. 243. So now with that in mind, let's take a look at something like this. 0.3 squared. Does 0.9 look correct? Okay, if you punch in your calculator, 0.9, you might be tempted to say that's the right answer, but if you punch it in your calculator, it's 0.09. Because remember, we got 0.3 times 0.3. 3 times 3 is 9, but we have to do 1, 2 decimal places in the problem. We have to have 1, 2 decimal places in the answer. When we multiply numbers, we combine counts, but we also combine the names. Tenths times tenths has to give us hundredths. So 0.04 squared. What's that going to end up as? 16 in how many places? 4. There's 2 places here. So it'd be 2 plus 2 or 4 places. So 16 10,000ths. You are correct. How about this one? Well, 5 to the power of 3 is 125. How many decimal places do we need? You've got 2 here, so you're going to have 2, 2, and 2 makes 6. So there it is, 0.000125 or 125 millionths. How about this? 2/3 squared. Well, this is going to be 2/3 times 2/3, right? When we multiply straight across. 2 times 2 is 4. 3 times 3 is 9. When we take a fraction to a power, this just becomes 2 squared on top, 3 squared on bottom. We can actually separate it out and do the numerator and the denominator separately. So if I have 5/8 squared, I can just view that as 5 squared over 8 squared, or 25 over 64. So if I have 2/5 to the power of 6, I treat that as 2 to the power of 6 over 5 to the power of 6. What's 2 to the power of 6? 64. 5 to the power of 6? 15,625. Now you look at that, that seems like a really weird number. I mean, 2/5 is 0.4, that's just less than 1/2. This is way less than 1/2. But if you think about this, if it were 0.4 to the power of 6, how many decimal places does this have to have? Well, this is 1 decimal place and it appears 6 times, so there's going to have to be 6 decimal places, right? Does that make sense? And 4 to the power of 6 is 4,096. So yeah, it gets small in a hurry. Remember, when we are multiplying, we have kind of a break-even point at 1. If I have some number, if I call it x, and I multiply by 1, I get back the same amount. It doesn't change it. Yes, sir?
No, I understand all this, but just to see it, like, say I'm doing there's a problem in the real world, and I'm like, hold up, how is that smaller when I'm timesing it by itself that many times? Why is it a smaller number?
Well, that's the one I'm explaining right here. Let's just pick a number like 8. If I multiply 8 by 2, it gets larger. It gets to be 16, right? If I multiply 8 by 1, it just stays the same as 8. If I multiply 8 by something smaller than 1, like 0.5, it gets smaller, 4. So we're used to multiplication making things bigger. But we have this break-even point right here at 1. If we multiply something by 1, it just stays the same size. 1 to the power of 273 is just 1. I can multiply 1 by itself as many times as I want to. It's never going to change from 1. I can multiply something by 1 as many times as I want to, and it's going to stay the same. If I multiply it by something bigger than 1, it's going to keep getting bigger, even if it's just slightly bigger. And if I have 1.1, that's bigger than 1, right? So if I multiply it by it, it's going to make stuff larger. If I take that to the power of, let's say I take that to the power of 10. So 1.1 to the power of 10. I get 2.59 rounded off. So even though 1.1 is barely bigger than 1, if I multiply by it over and over again, it's still going to get bigger.
Cool. So if I have to take 7 cuts of 0.49 off of my part,
yeah, but you're
off more.
Well, you're looking at multiplication though. You're looking at multiplying by 7 cuts of 0.49. You're taking 0.49 times 7. The 7's bigger than 1. So you're going to be bigger than 0.49. Yeah. If you're multiplying by 0.49 several times, then it's going to get smaller.
Right.
Let's say you're looking at a shrinkage factor, where for every degree of temperature, like I said, I can't think of any metals that would continue to shrink, but for certain polymers, for every degree of temperature, the temperature drops, it shrinks to 0.98 of its original dimension. So let's say it decreases by 6 degrees. So it's 0.98 to the 6th power is what you've shrunk. come on. You're down to 0.886. So you've lost 12% almost. The best example I can see of this is reliability. Let's say you build a machine that has 200 parts in it. And each part that you put into that machine is 99% reliable. 99% reliable sounds like a pretty good reliability, right? How likely is it that that machine will perform its function without malfunctioning? Without at least one part malfunctioning? Well, 0.99 to the power of 200. There's a 13% chance. 0.134. 13.4% chance that machine will function without at least one part malfunctioning. That's pretty low. So you can see there, I mean, 0.99 is just slightly smaller than 1, but we multiplied by it 200 times. So, I mean, how about 99.99% reliable? Would that make it better? Well, obviously it's going to make it better, but is it now acceptable? I mean, it's not acceptable to only have a 13% chance of your machine working right. So if every part is 99.99% reliable, there's 200 parts. Now you're up to 98%. That might be acceptable depending on what it is you're doing. Still having a malfunction 1 out of 50 times might not be acceptable. But that's just that power of repeatedly multiplying by something. It's the same the other way around. If you have an expansion, that compound interest. Let's say you've got something that's going to grow 1% a month. So it's going to be 1.01. And you're going to let it sit there for 10 years. Well, that'd be 120 months. So it's 3.3 times what it started out as. So that 1% looks small, but again, if it grows enough times, it grows significantly. So that's basically it, is the fact that if something smaller than 1, it's just going to keep getting smaller. If it's larger than 1, it's going to keep getting larger. And of course, at 1, it stays the same size. So now we have to be able to go the other direction. Every operation we've looked at so far has its inverse, its reverse. When we multiplied, actually, let's look at addition and subtraction. We had addition and subtraction. We said they were the same operation. One was going forward and one was going in reverse. So let's say I have 7. Pick any number to start with. Let's say I'm going to add 4 to it. 7 plus 4 is 11. If I want to get back to the 7, what do? I subtract the 4. Adding and subtracting are inverses. If I add a number and then subtract the same number, I get right back to where I started. I have the same relationship with multiplication and division. If I start out with a number, let's start out with the 7 again. This time, let's multiply it by 4. We get 28. If I want to get back to the 7, I would divide by 4. So the same thing here. Multiplication and division are inverses. If I multiply by a number and then divide by the same number, I'm going to get right back to where I started. Well, these powers we've been talking about are just another operation. So if I have 7 to the power of 2, 7 squared is 49, I have to be able to get back to 7 somehow. How would I do that? Square root. The square root of 49 is the reverse of squaring it. The square root of 49 is 7. When you see that symbol, its technical name is called the radical symbol, but we know it mostly as the square root symbol. All it's asking is, what number squared equals what's inside of it? In this case, 49. And we know 7. But we know there's also another number that could do it. What other number squared could be 49? -7. So whenever we take a square root, there is a possibility of a second answer. Now in the real world, usually that negative answer is not significant. Usually we're dealing with positive dimensions and stuff. But there are some cases in architecture and even in machinery, if you get into force analysis, strength of materials, there are some times where you're looking at the negative root can actually be the spot where you have your maximum stress if you're trying to solve an equation. So you do have to be a little bit careful with that. It can come out to be that negative root to give you a location. Let's take a peek at square root of negative 64. What's that going to be? Can't do it. Why not? Yeah, because you got to remember, this is asking us what number squared equals negative 64. What did we just say about numbers when you square them? The result is always positive. Because any number times itself will be positive. A positive times a positive will be positive. A negative times a negative will be positive. So there is absolutely no number that we can square to get a negative number. So if we try to take a square root of a negative, your calculator will tell you error. It'll say you can't do it. What's that symbol mean? Cubed root. That is now saying, it's rather than square root, it's saying cubed root. It's asking us what number to the power of 3 was 8. It was a 2. 2 to the third power is 8.
How do you put that in your calculator?
That's where we're going next. On your calculator, you've got your power key, your caret key. Generally, it's right above that. There should be something that looks like that, either X root or N root, like that.
It's the same key as the press second.
So yeah, you should say,
You gotta press 3.
should play second. Depending on your calculator, some of you have to press second, some of you have to press third. Or some just shift. But for your calculator, you'd type in the 3, then you'd hit that button. You have to do shift in that button or second in that button. And then you would type in the 8 and hit equals. It should spit out the 2. Okay, so what if I want to take the fourth root of 625? So what you get? You get 5? Perfect. How about the fourth root of negative 81? Gives you an error, doesn't it? Remember, that's asking us what number to the power of 4 equals a negative 81. Anything to the power of 4 is going to be positive. How about a third root of a negative 64? Try it. How come we can do the third root and not square root or fourth root? Because it's an odd number, it's not a power. Odd powers can give us negative results. Comes out to be a negative 4 here. So since an odd power can give us a negative result, we can do an odd root of a negative number. It works out.
What about 4?
Fourth root? A fourth root of, let's do
64.
negative 64. Yeah, I won't let you do it. It's going to give you an error because, again, that's an even power. Yes. If I wanted to do a fifth, actually that would be a complex number. Imaginary numbers can only come from square roots. But you can some higher roots you can simplify to square roots. So anyway, a fifth root, if you want to do a fifth root of, let's say, a negative 32, see what that comes out to be. Oh, you got to hit the second. So you've got to do 3, shift, and then that, and then the negative 64. No, you got to hit that. This is one for you. And you got to do shift. You can see the roots are above it there. What'd you get for that? Fifth root of negative 32. Negative 2. Perfect. Okay. So how about, without punching your calculator, what would you say for the square root of 0.9? A lot of people would just yell out 0.3, but it can't work, can it? It's 0.3 squared is 0.09. Square root of 0.9 is going to give us something really ugly. 0. What? 98. 94. Okay. 949. We'll call it for now, approximately. When we're used to square rooting something and getting smaller items, but when we square root a decimal, remember, if you square a number that's smaller than 1, you get an answer that's smaller, right? If I have 0.3 squared, well, I got it right here, it's 0.09. It gets smaller because this was smaller than 1. So when I square root something that's smaller than 1, it has to get larger. I take the square root of 0.16, that's going to be 0.4. Or I might try...
How would you do that without a calculator?
Without a calculator? Good question. How would you do a square root without a calculator?
Divide.
No, you can...
Plug and play, kind of?
Well,
Look at a chart of that.
there are charts that you can use. There is a process. You want to see the process for square root? Let's see if I can remember how to do it. Give me a number, 5 or 6 digit number. 734. How's that? Notice I put it in groups of 2s. Starting from my decimal point, I have to do it in groups of 2s going back. Okay? So now I look at this first group of 2, and it might just be one number in the first one. If it was 5 digits, it would only be one number up there by itself. What is the largest number that has a square less than 24? Well, 5 squared would be 25. That's too big. So it's going to have to be 4. 4 squared is 16. Okay? So, trying to remember now. I got to take a peek. I haven't done this in a long time.
You know me, man.
Yeah, no question. You know how to ask. It's complicated. What is it? Like, oh, holy calculator, I worship you. Like, yeah, this is too hard.
So I'm trying to make sure I get everything correct here. What are they doing is it doesn't work.
Put the square root of 4 in there.
This algorithm is not what I'm used to seeing, so I'm going to try a different one. Okay, so here we go. Okay, so we did the 4. 4 squared is 16. We subtract, we've got 8, right? So we're going to bring down 87. Now 20 is a constant that is used. So we take the result we have up here times 20. 4 times 20 is 80. Okay. So now we have to use 80 plus x times x. That has to stay smaller than 887. So if x is 1, this is 81 times 1, which would be 81. Well, that's obviously smaller than 800. So it's going to be bigger than 1. So I'm just going to put in numbers and try it. So if x were 5, this would be 85 times 5, which is 425. So that's too small. If we try, let's try like a 7. 87 times 7. That's too small. 88 times 8. That's too small. 89 times 9. That's actually going to work. 801. So I put 9 up here. 801 goes down here. I subtract. This is 86. Bring down the 34. Well, now I take the 49 times 200, or times 20, I should say. 49 times 20 is 980. So now I've got to use 980 plus x times x to get 8600. Well, I'm looking, let's try 9 again. 989 times 9. 8901, that's too big. So 988 times 8 is 7904. That's 8. We're going to subtract down here. So 0, 3, and 7. So now we're at the decimal point. I put a decimal point up here, and I got to add 2 zeros at a time. We got to do pairs. So now I'm taking 489 times 20. 498, sorry. 498 times 20 is 9960 plus x times x. And it has to stay less than 73,000. Let's try 7. 9967 times 7. It's going to work. 69,769. I'm going to stop there and I'm going to show you. Let's check and see if I made this work. 24,
Yeah, that's right.
87, 34. That's right. Yeah, 498.7 and keep going. The more digits you get into it, the worse it gets because this number here keeps getting bigger and bigger and bigger and bigger. And it's a real struggle. Yeah. Maybe on one of your tests, I might give you an extra credit question of calculate the square root by hand.
It'll be blank.
It'll be blank. I mean, even here, I cheated and used the calculator. I mean, I could have done it without the calculator, but it would have been a lot of paper trying. Okay, 87 times 7, 88 times 8. I mean, it would have got it out, but it'd be a lot of scrap paper to do it.
So is that what they did before calculating?
Oh yeah, but they have tables as well too, and you look up in the tables of what you do is you look up perfect squares and then see, oh, okay, there it is. So then you extrapolate in between. So let's say 498 squared is 24,000 something. 499 is 25,000 something. So 24,000 or actually 248,000, I should say. 734 is between those two. So then you extrapolate in between them as to how far. And yeah, it was not. I mean, I've had a calculator my whole life. There's never been a period I can remember not having a calculator. I mean, they didn't let us use them in elementary school. It was middle school before they let us use them, but still, I've always had one.
We weren't even allowed to use calculators.
You weren't? Oh, that sucks. We had certain things we could use them for and certain things we couldn't.
I mean, there was like very rare nights at class.
Yeah.
Yeah, they made us write everything on.
You walk to school uphill in the snow too. So.
I was gonna say he remembers that one day that it was raining and snowing and icy, and he tried to walk to school.
Like, if it was a big problem.
Every time he took one step forward, he'd slide 2 steps back. He would have never made it to school until he gave up and turned around and tried to walk home, and he slid backwards right to school.
Like they would let us use calculators on big problems, but we still
Yeah.
had to do it every.
Had to show all the steps of your
Yeah.
calculations. Yeah.
So it was like you didn't use it anyway. Like you could get the answer, but you still had to show it.
Yeah. I understand. I just have to pick on you because I can't.
I mean, I did walk uphill both ways.
Okay, so in your book, page 121, 123, it's exercise 3-17. There's some word problems dealing with powers and roots. So page 121 through 123, exercise 3-17.